Okay, so we'll start this lecture by looking at some special matrices, or matrices that have a specific shape to them. So, upper triangular matrices are square matrices with zeros below the main diagonal. So the main diagonal of a matrix is this diagonal. With upper triangular matrices, we require that everything below the main diagonal is 0. So this has to be 0, this has to be 0, this has to be 0. Okay? So the entries, the other entries, so these entries can be anything. Okay? The only requirement is that everything below the main diagonal is 0. So we always create matrices like this when computing the reduced for echelon form of a square matrix. We get an upper triangular matrix of that. Lower triangular matrices are the opposite. They're square matrices with zeros above the main diagonal. Okay, so here we want this to be 0. Here we want these to be zeros. Okay. So observe, if you take the transpose of an upper triangular matrix, you'll always get a lower triangular matrix, and vice versa. So diagonal matrices now are square matrices that are both upper and lower. Okay, so you look at the main diagonal, and then you force everything above and below it to be 0. Okay, so the only potentially non-zero entries are the diagonal. So here are two examples of diagonal matrices. The identity matrix, denoted I subscript n, is an n by n diagonal matrix with ones along the main diagonal. Okay, so the 2 by 2 identity, ones along the main diagonal, zeros elsewhere. The 4 by 4 looks like this, and so on. Okay, and the identity matrix has the property that when you multiply it by any other square matrix of the appropriate size, you just get that other matrix back. So A times I is A. I times A is A. Okay. So it's like multiplying by 1 in real numbers. Then there are symmetric matrices. Okay. So these are matrices that are square and are invariant under transpose. In other words, when you transpose them, they don't change. So A transpose equals A. So here are two examples. Okay. So if I take the transpose of this matrix, I swap its rows and columns. Okay. Then this matrix will be the same. Same with this matrix here. Okay. So the entries that are like across the diagonal like this have to be equal. These entries have to be equal. 2 and the 2, and 3 and the 3 have to be equal. Notice with symmetric matrices, it doesn't matter at all what's on the diagonal. It just matters what's across the diagonal, that they're exactly equal like this. So symmetric matrices will be very important later in this course. Let's review some properties of matrix multiplication. Just as a reminder, here's the definition of matrix multiplication. So we're going to use it. So we have A times B. We think of B as its columns, B1 through BP. And then to compute the product, A times B, the first column is going to be A times the first column of B, and then the second column of the product will be A times the second column of B, and so on. Okay? So that's the definition we've been using. Okay? So here are some facts about, or some properties about matrix multiplication. Okay, so the first property is that it has an associative law. Okay? So what that means is if you have A, B, C, okay, you can bracket it off as you like. In other words, you can compute BC first and then multiply it times A, or AB first and then multiply it by C, and you'll get the same result. Okay? So that's as expected. So B and C describe a distributive law for how matrix multiplication interacts with matrix addition. Okay? So it's different for matrices than real numbers, okay? Because the order in which you multiply matrices matters. Okay? So suppose you're multiplying A times B plus C. So if you want to distribute this, you have to write it as AB plus AC. Okay? So since A is on the left here, A has to be on the left for AB and on the left for AC. Okay. What you can't write for this is have this expression equal BA plus CA. Okay. You have to retain the order when expanding on this. And conversely, if you have an expression like this, and you see, oh, I have an A here, both of them, you have to factor it out on the left-hand side. Okay? So for the right distributive law, it's saying the same thing, but on the right, essentially. Okay? So if you have a sum here, B plus C, and you're multiplying on the right by A, then when you distribute it, you have to keep A on the right. So order matters when multiplying matrices. Part D is saying that if R is a scalar, you're free to move it around the equation, if it's a factor in a multiplication like this. Let's talk about some properties of the transpose operation. Okay, so remember the transpose flips the columns and the rows. So we mentioned this before. If you take the transpose of the transpose, you get your original matrix back. Part B here is saying if you're taking a sum and then you transpose it, that is equal to taking the transpose of each of the sums. Okay? And C is saying that scalars aren't affected by transpose. So D is the thing you need to remember about transpose operations. So when you're taking the product of a transpose, A times B, you put the transpose on each of the factors. You have to reverse the order. Okay? So if you had an even longer string of multiplications here, say it was A, B, C, D, then you would have to reverse that entire string and take the transpose of each one. So it'd be D transpose, C transpose, B transpose, and A transpose. Okay, so now we'll give a few warnings about matrix multiplication. Okay, so as I said before, the order in which you multiply matrices matter. In other words, A times B is not equal to B times A in general. For some very specific matrices, this will be true, but if you just choose a random A and a random B, it won't be true. Okay? So there are two main things I think that make matrices different from real numbers when you're solving equations of matrices. Okay, the first thing is that the order in which you multiply matters. Okay? And the second thing is that not every matrix has an inverse. Okay, so here's a consequence of that. Okay, so if you have AB equals AC, then in general you cannot conclude that B equals C. Okay? So if these were real numbers, right, you would just cancel out the A's. Right? You can't do that with matrices. Okay? The exception is if A is an invertible matrix, then you can do this because you can multiply this matrix on the left. You can multiply this equation on the left of both sides, so that multiply it by the A inverse. That will cancel out. That will kill the A's on both sides. Okay, we'll get into inverses of matrices after this. Okay. So, in general, that cancellation will not work. Exception is when A is invertible. Okay. So another thing you can't do with matrices that you can do with real numbers is that if you have the expression AB equals 0, then you can't conclude that 1 of A or 1 of B is 0. Okay? With real numbers, if you had xy equals 0, then you can conclude that at least 1 of x or y is 0, but not for matrices. So here's an example that shows this. If A is this matrix, okay, just a 1 in the top left, and B is this matrix, just a 1 in the bottom right, then the product is the 0 matrix. But neither A or B is the 0 matrix. So you can't conclude that. And the last warning is about taking powers of products. Okay, so if you're taking the power of a product, say you have A times B, and you're trying to raise it to the power K, then you can't write it as AK BK. You can do that with real numbers, but not with matrices. The correct way to evaluate this is like this. Okay, you just literally write out AB K many times over and over again, like this. So this is K many ABs. And the reason this is not equal is essentially because matrix multiplication does not commute, which is what this is saying. Now we'll talk about invertible matrices. Okay. So here's a definition. So first of all, we're talking about square matrices. Okay. Only square matrices can be invertible. Okay. So square matrix A is invertible if there exists another square matrix of the same size, call it B, such that A times B is equal to the identity, B times A is equal to the identity. So if such a B exists, we write that B is equal to A to the power negative 1. And we call this the inverse. Okay? And so not every square matrix is invertible. Some of them are not invertible. Okay? So if the inverse exists, then it's unique. Okay? So if you've found a B that satisfies this, okay, then that's the only one that will do it. You don't have to worry about another matrix having that property. So inverses are unique. Okay, so now we'll look at what's called the invertible matrix theorem. Okay, so this is a theorem that thoroughly categorizes or characterizes invertible matrices. Okay, so this is then the following are equivalent type theorem, okay, which means that for a matrix A, there are only two possibilities. Okay? Either all these things are true, or none of these things are true. Okay, and the first of them is that A is invertible. Okay? So if you want to show that A is invertible, you can test any one of these things, and if it's true, then A is invertible, and everything else on this list is invertible. If anything on this list fails, if it's not true, then A is not invertible, and everything else on this list fails. Okay, so here are some nice properties that we've encountered before. Okay, so we want the columns of A to be linearly independent. We want the rank of A to be n. Okay, we want the reduced row echelon form of A to be the identity. We want AX equals B to have a unique solution for every B in Rn. We want the homogeneous system to only have the trivial solution. Right? That's equivalent to B. We prove that. And the rest mostly have to do with stuff we haven't explicitly talked about yet. Okay, so I'll just say what they are. We want the column space to be all of Rn. Okay, we want the null space to be only the zero vector. We want it so that 0 is not an eigenvalue of A. Okay? So if 0 is an eigenvalue of A, we know A is not invertible. Okay. Did I say that right? So if 0 is not an eigenvalue of A is invertible. Okay. So the converse of that is that if 0 is an eigenvalue of A, then A is not invertible. That's the correct way to say it. Okay. We want that the determinant is non-zero. Okay. And we want the transpose to also be invertible. So we've done a lot of the work to sort of show that these first couple ones are interchangeable already. You can look in the book to see the details worked out, and we'll get to the rest of these as we go along in lectures. So we haven't talked about what the determinant is or what an eigenvalue is. Okay, so we have a square matrix A. Sometimes it's invertible, sometimes it's not. We have a bunch of tests that are equivalent to it being invertible. Okay. So what are some ways to calculate exactly what the inverse is? Okay. So for a 2 by 2 matrix, it's not too bad. Okay. So if we let A be this matrix here, little a, b, c, and d, then the determinant, if the determinant, which is AD minus BC, if this is non-zero, then the inverse exists, right, by this theorem up here. Okay, I'm just telling you that this is the formula for the determinant of a 2 by 2. So suppose it's non-zero, that will mean A inverse does exist. Okay. This is an explicit formula for A inverse. Okay. Have A, what do? You swap D and A. You multiply B and C by -1. And then you multiply the whole matrix by this scalar, which is 1 over the determinant. Okay. So that's explicit formula for computing the inverse of a 2 by 2, if it exists. Okay. If it doesn't exist, then the determinant will be 0, and then this will be undefined, and you won't be able to calculate it, right? Okay, so I think this is a part of the invertible matrix theorem, but it's good enough to state on its own and give a short proof of. Okay, so let's assume A is an invertible n by n matrix, and think about the equation AX equals B. Okay. For each B in Rn, we have a unique solution that has this formula to it. Okay. X equals inverse of A times B. Okay. So how do we get that? Okay, so here's a short proof of how we get that. So if we start with AX equals B, okay. Now since I'm assuming that A is invertible, I know that A inverse exists. Okay, and I want to isolate for X here. So I can achieve that by left multiplying this equation by A inverse. Okay, so both sides of the equation, I multiply on the left by A inverse. So whenever I multiply an equation by a matrix, okay, I have to decide, am I going to multiply it on the left, or am I going to multiply it on the right? Okay. And I have to do it consistently on both sides. But I decide to multiply it on the left. Okay, and that gives me what I want. Because on the left now, I have A inverse times A. And that just equals the identity, right? And then, so the identity here times X is just X itself. So that effectively isolates for X, and so X equals A inverse times B. So in this situation, the real hard part is computing A inverse. Okay. So we know how to calculate for the inverse of a 2 by 2. How do we do it for bigger matrices? Okay. So what we want to do is remember how we solved AX equals B originally. What we did is we formed an augmented matrix like this, and then computed the reduced echelon form. If A was invertible, then we got a nice solution, right? If A was invertible, then we got the identity matrix where A used to be in the reduced echelon form, and where B used to be now is the solution to AX equals B. Right? We could read the solution. We could read the solution for X right off of here. Okay, so that was the strategy for solving AX equals B using the augmented matrix. And the same thing works for finding the inverse. Okay, so now the equation we're trying to solve is AB equals the identity, right? We're trying to solve for this B. What is this matrix that I multiply A by so that the result is the identity? So B is the unknown here. Okay, so what I'm going to do is form the matrix A and the identity over here. Okay, the identity takes the role of B now, where that's the thing I want to equal. And then I put it in reduced echelon form. Okay, so if A is invertible, then we'll get the identity matrix on the left side now. Sorry, we're over here, we'll get the identity matrix. Okay, A will turn into the identity matrix when we reduce it. And what pops up over here is the solution, the inverse of A. Okay, so see how when we were solving this, and A was invertible, the solution X showed up over here. And now, the solution for B, which is what we want it to be A inverse, right, pops up over here. Okay, so if A is not invertible, if you try to do this, it won't help you. Okay, you won't get the identity over here, and it just won't work. Okay, so this will work. This method will work for finding the inverse of A for any size square matrix, provided the inverse exists, of course. Okay. And this method is usually a lot of work to do by hand. So now I'll just mention some properties of the inverse. Okay. So let's assume A and B are invertible. So the first property says that if you take the inverse of the inverse, it's just A again. Okay. In other words, it's saying that the inverse of A inverse is A. And that makes sense, right? What do you multiply A inverse by to get the identity? A. So this makes sense. Part 2 talks about taking the inverse of a product. So it's a similar rule to the transpose. In fact, it's the same rule, right? Taking the inverse of a product, put the inverse on both of the factors, but you reverse the order. Okay. And part 3 tells you how inverse and transpose interact. Okay. So if you're taking the inverse of the transpose, it's equal to taking transpose of the inverse. So you can just switch them here if you want. Okay. So let's talk a bit about the determinant. So the main motivation for us for looking at the determinant is that, as we mentioned before, in the invertible matrix theorem, it's worth repeating here, that A is invertible if and only if the determinant is non-zero. So the determinant is a number. Okay? It's a number associated to a matrix. So how do you compute it? So the determinant of a 2 by 2 is just AD minus BC. Okay, so it's simple to compute for a 2 by 2. For larger matrices, it's a bit more work. Okay, so here's an example of how to compute the determinant of a 3 by 3. Okay, so what I'm using here is called Cofactor Expansion. Okay, so I'm expanding along the first row. So I take the first entry in the first row and I multiply it by the determinant of this part. And then I subtract off the second entry in the first row and then multiply it by the determinant of, it's sort of hard to describe, this matrix here. And finally, I take the third entry and then multiply it by the determinant of this 2 by 2. So that's an example of how you can compute the determinant of a 3 by 3. Okay. So if you don't remember how to do that, I suggest you just look in the book under Cofactor Expansion in section 3.1. And you can use cofactor expansion to compute the determinant of any size square matrix. But for this class, we'll mostly be looking at 2 by 2s and 3 by 3s for computation. Okay? Okay, so some matrices have really easy determinants. Okay, you don't need to do this cofactor stuff. Okay. So triangular matrices, you can just read off the determinant quite easily. Okay. So if A is triangular, upper, lower, or both, so diagonal is included as well, then the determinant of A is the product of its diagonal entries. Okay. So that's a nice easy computation. Here's some examples. So this is an upper triangular matrix, right? So the determinant A is 1 times 5. This is upper triangular. Determinant A is the product of the diagonals. This is a diagonal matrix. So the determinant is the product of its diagonal entries. So finally, we'll mention some determinant properties that are helpful to know. So if we let A and B be square matrices and K be some scalar, then the determinant function has it's called a multiplicative property. So if you take the determinant of A times B, it's equal to the determinant of A times the determinant of B. This is very helpful to know. Another property is that the determinant of the transpose is equal to the determinant of the original matrix. The third property here describes how you can take the determinant of a scalar times a square matrix A. So what you have to do is, or what you can do, is factor out the K from it. And if you do that, you raise it to the power n, where n is the size of the matrix equation that you're working with. So if A was a 3 by 3 and K was some number, you take the K out and raise it to the power 3. Okay. Now, if A is invertible, then taking the determinant of the inverse of A is equal to 1 over the determinant of A. Finally, we'll end with a warning that although the determinant has a nice multiplicative property, it does not have a nice additive property. Okay? In general, the determinant of a plus b is not equal to the determinant of a plus the determinant of b.